Okay. So now we come to a different partition equation or parameter. We will deal with soil water partition coefficient, which is normalized to the organic carbon KOC. This KOC is defined as the ratio of the mass of the compound adsorbed per unit weight of organic carbon on soil divided by the concentration of the compound in a liquid aqueous phase. It will give you the microgram per gram of organic carbon over microgram per ml of water, or milligram per kilogram of organic carbon, or milligram per liter of water. This is dividing by each other, and that's what gives you KOC. If you could look that this is the soil and this is the water around it. See the water around it? So the partition between the water and the organic and the solid back to the water, we could call this KOC. It will model the soil water partition. And also in KOC, we have to account for the fraction of the organic matter. Now, in this soil, not everything in this soil is 100% organic, okay? Now we have to account for what is the fraction of the organic carbon. FOC times KOC is equal KD. And here, now, this KD is used a lot to see the partition between soil and water, okay? So KD is microgram per gram in soil. So if you have, let's say, if you have sand and if you have water, this is water and this is sand, and let's say another sand, another water here. You know, I'm talking about the pores of the water around the sand particle. So microgram of organic in the soil per gram of the soil, microgram of the organic in the soil per gram of soil divided by, now we go to the water, microgram of the organic in water over the milliliter of water, okay? So this is equal to KD equal FOC times KOC. KD is equal to what? Concentration of the organic in the soil divided by the concentration of the organic in water. Concentration of the organic in soil divided by the concentration of the organic in water. Okay? And these are the meaning of each one of these parameters. We finished KOC, and we said that not all the soil has 100% organic, so we have to add a fraction of organic carbon, and then we find KD. Now we are still soil to water, water to soil, the transfer of the organic from solid to water and water to solid back. Now there is another partition coefficient called octanol water partition coefficient, KOW. This is which is a measure of hydrophobicity of a compound, which, you know, if you remember back in chemistry, it will measure the repulsion of the water, nonpolar versus polar, which one is tend to dissolve more in nonpolar than in polar solvents like water, which at the end like dissolve like. I don't want to go into the definition of this. You could check your chemistry levels, but KOW is a measure of hydrophobicity of a compound. Now, why we have to study KOW? KOW, it is the concentration of the compound, the organic, in the octanol water, and divided by the concentration of the organic compound in the water molecules. So you will, it's like a tube like this. You'll have water, you'll add octanol, and then you close the flask, and then you shake it, and of course there is organic inside the water. And then later on, once you shake it, you can see that you will have octanol at the top with a lower density and water at the bottom, octanol and water. So you can see how much organic here divided by how much organic here, and that is KOW. The main objective why we are doing KOW, because KOW, the greater the KOW, the greater the tendency to partition into the octanol phase. If you have higher KOW, all the organics gonna go from the water to the octanol phase. What is the meaning of this again? KOW, it will tell you that it will be absorbed into the organic carbon in soil. Very easy. If you have water, it will, if you have higher KOW, it will absorb in the organic carbon in soil. It will go from water to soil directly. Same thing, if you have high KOW, it will accumulate in the fat tissue of fish. We call it PCF, and this is KOC. Let's say, for example, if you have a tank, and this tank has a fish, and this is, of course, seawater. And let's say that one of these chemicals in table 3.1, let's see if I put this chemical, benzene. Benzene has a log KOW of 2.17. Let's compare it. Benzene versus this chemical. Okay? Which one of these, if found in seawater, will accumulate in the fish tissue easier and quicker? Of course, this one. The higher KOW, which means it will accumulate in the fat tissue much quicker, and most of it will go in the fish tissue. But if you go to this smaller one, 2.17, it's not that small, it's still high. Benzene will accumulate, that's for sure. But let's say if you go to benthelic acid, 0.73, it will accumulate less. While this, it will accumulate so fast. Okay? It means that the transfer from, if you have, for example, solid and water on top, if you have this chemical, it will go from water to solids quicker. If you have this chemical, it will still stay in water, and it will go to solid, but at very slow and small amounts. Okay? There is a correlation between KOC and KOW, and this is the equation that we use a lot. If you have KOW, you could find KOC. You can see how small, how big is R square. And of course, this is for N72. If you plot log KOW versus log KOC, you'll end up with a straight line. And of course, this is good for some certain chemical, not for all chemicals, for certain chemicals. Because other chemicals, depending on what type of chemical you're talking about, how many chlors that this chemical has, this equation will change. But for this class, we'll only teach this equation. In the master's degree, this equation would be much bigger. So, remember the equation that KD, soil to water, is equal KOC times FOC. KOC here is equal KD over FOC. Let's look at this equation. That's very easy. You have log KOW, and you want to find the anthracene soil water partition coefficient normalized to the organic carbon, KOC. You could find it if you have log KOW, 0.903 plus 0.094, 4.32, and you could find KOC, 10 to the power 4.32. This is also another example that we mentioned in class, and we could repeat this one more time. Anthracene has contaminated harbor sediment, and the solid portion of the sediment is in equilibrium with the pure water if the organic carbon content of sediment is 5%. So, this is FOC, 5%. The solid sediment anthracene concentration is 50 microgram per kilogram, okay? Sediment. What is the pore water concentration? Now you have the soil, and you want to know now the water concentration of that anthracene at equilibrium. Of course, we did find log KOC from the previous example 4.32. We did this. Okay, so now let's find out KD, because we need KD for the equation itself. So we need KD. KD is equal to what? Remember KD? FOC times KOC. And KOC, we have it here, 4.32. So 10 to the power 4.32 times 5%, 0.05. This would give you 1045. So this is KD, 1045 centimeter cube per gram. And also remember that KD is equal to what? C in the solids over C in the water. The concentration of the organic in the solids versus the concentration of the organic in water. Now, what is the concentration of the solids in the organic in solid is 50 microgram per kilogram. So 50 microgram per kilogram. Of course, here we're going to convert kilogram because we need to make it as consistent with the other units. So we'll do this later on. Divided by the concentration of divided by seawater. Well, that's what we need. KD is given. KD is given here, 1045 centimeter cube over gram. So you have seawater is equal 50. You can see it here. Times, you convert the kilogram to gram, now microgram per gram, divided by centimeter cube over gram sediment. Okay, and the centimeter cube, you convert it to milliliter. You put it over there, so 1, and this is centimeter cube, go with centimeter cube. Now you have milliliters. Milliliter, you convert it to a liter. 1 liter is 1000 milliliter. Now you end up with what? Now you end up with what? Now you end up with gram. This is gram with gram. You end up with microgram over liter. That is 0.048 microgram per liter. This is the concentration of the organic in the water. Remember, we said that milligram per liter is equal ppm. That is milligram, and that's microgram. This is equivalent to what? 0.0. This is equivalent to, this is the concentration of the organic in the water, 0.048 microgram per liter. So now, this is where we did the sediment phase concentration. So this is equivalent to 0.048 part per billion. Remember, we mentioned that if it's 0.048 milligram per liter, this is equivalent to 0.048 ppm. But since this is microgram, you have to bring it down to part per billion. Okay, so this is equivalent to part per billion. So the concentration of the organic in water is 0.048 part per billion. And of course, this is by mass. And you could see the concentration of the organic in the sediment. It was 50 microgram per kilogram. 50 microgram per kilogram, you could convert it, milligram per kilogram is ppm, but since this is microgram, this is 50 part per billion. So you can see the concentration of the organic in the solid is 50 part per billion, while the concentration of the organic into the water is 0.0488 in the water itself. Of course, this is because anthracene is hydrophobic. Okay, لاحظ, make a note of it, that most of the organic went to the solid. Nothing stayed in the water, very small amount. That's why we call it the anthracene is hydrophobic. Its aqueous solubility is very low. It will not love water, does not love water. KOW here is very high. Okay, if you look at KOW, it is very high. So it will prefer the solid phase. It does not like water phase. Okay? We'll talk about this anthracene later on because we're going to use this for other treatment later on. This is also a very important example that we will be mentioning this in the next video.